John Warnock was working at Xerox PARC in 1978. He was developing a graphic page description language for plotters. Now, a plotter is something like an electrocardiogram or a seismograph where some sort of input causes a needle or a device with a pen on it to move around as paper goes through it. And that's pretty much how a lot of our printers still work today, although they are driven by a page description language which did not exist before John Warnock. If you've seen the printers in the print shop at Columbia in the 623 building on the first floor, these are basically plotters. Paper goes through it and a computer tells it what to do with heads that spray different colors of ink onto the paper. That's basically a plotter. But to draw pictures with a plotter was only possible because of John Warnock's work at PARC. In 1982, he formed Adobe Systems with Chuck Geschke, and in 1983 they released the Adobe PostScript language, a page description language that allows us to do all of this stuff on the computer. Everything you see on this page and everything I've showed you has been put together through an Adobe PostScript process. The pictures, the words, the type, the description of the typography, how the fonts are defined, all of this is dependent upon the PostScript language, converting what we do in terms of coding or input on the computer into something that can be output to a printing device or other output devices such as a computer screen, a projector. In the world of offset printing, for outputting film or paper that is used to print pages, or outputting to film that's used to burn printing plates, or we actually now do exposure direct to plate. But it takes an Adobe PostScript RIP, raster image processor, to convert the data that is in your computer into a linear code of on and off signals to tell the laser how to expose the plate or the film, and that's the key to it, is the PostScript RIP. 1984, Apple LaserWriter was introduced. $9,000 for a desktop printer at 300 dots per inch, which is really, really low resolution by today's standards. Your typical $50 black and white laser printer today probably has a resolution of 2,400 dots per inch. But 1984, this was a big deal that we could have that kind of quality in a PostScript printer on your desktop. 1985, Linotype had been working on Cora language, but chose a PostScript RIP for the Linotronic 100 and 300 and licensed Mergenthaler fonts to Adobe. Mergenthaler Linotype Stempel Haas was the largest type library at the time, with over 1,400 fonts digitized for Densi and Cora, which then had to be redigitized for the PostScript language. Today they have, 20,000-30,000 fonts. Bit, from Wikipedia, the free encyclopedia. Now, I have to warn you that when I ask questions on a quiz or an exam, I'm expecting answers based on what I tell you, not what's in Wikipedia. If you get your answers from Wikipedia or just a web search online, the first thing that comes up may not be the answer I'm looking for. One example is RIP. If you look it up online, the first answer may be routing information protocol, which certainly pertains to computers, but it doesn't pertain to the graphic arts. In the graphic arts, RIP is raster image processor. A bit is a binary digit, a numeral in the binary numbering system, or base 2 digits, wherein each digit has a possible value of either 0 or 1. And if you look at the power switches on most devices today, it indicates when it's on and off with a 0 and a 1. 0, it's off; 1, it's turned on, because it has two possible states, on or off, 0 or 1. That's binary. Binary is anything that has only two possible states. A bolus hook on a Jacquard loom could either be up or down. That's a binary state. It's determined by a hole in a card, and that's either a hole or no hole. Hole or no hole, up or down, on or off, binary. Binary digits are almost always used as the basic unit of data, information, communication, and storage in digital computing and digital information theory. Well, that's true. Byte. Now here it gets a little tricky. A byte in computer science, a byte is a ubiquitous unit of storage measurement. Well, yeah, it is, but the more important thing is that it's a unit of data which may or may not be stored. You have an 8-bit keyboard. 8 bits is 1 byte. Every time you press a key on your keyboard, a byte of data is generated. It may be stored. It may not be stored. It may just be running around inside your computer. It may just be processed and ripped to your screen without actually being stored anywhere. A byte is data which may be stored rather than a unit of storage. Originally a variable number of bits smaller than a word, the popularity of IBM's System 360 starting in the 1960s and the explosion of home computers based on 8-bit microprocessors in the 1980s has made obsolete any meaning other than 8 bits. You see, I highlighted that because if I ask you what a byte is, it's 8 bits. The term octet is widely used as a synonym when greater certainty that 8 bits is the intended meaning is desired. Well, these days I'm pretty sure most people say byte, they mean 8 bits. I don't think you need to say octet to get that extra certainty. Binary memory system, a byte is 8 bits. 8 bits means that it's 8 columns of numbers. In decimal, such as you are more familiar with, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, first column is 0 through 9. Second column would be tens column. Third column is thousands column, and then 10,000s, 100,000s, millions, etc. In binary, since there's only 2 possible answers for what is in each of these columns, like the ones column, it's either 1 or it's 0. The twos column, if you have 2, it's either 1 or it's a 1. If you don't have 2, then it's a 0. Fours column, 8s, 16s, 32s, 64s, 128. So this is 1, 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth, 2 to the fifth, 2 to the sixth, and 2 to the seventh, and 2 to the eighth would be 256. There are 256 possibilities for numbers that you can describe in 8 bits. And the numbers are 0 through 255. Because it was 256, that would require a 9th column or a 9th bit. This is an example 1001111. You would add 128, 16, 8, 2, and 1, and that would give you 155 in decimal. Hexadecimal is another system that you don't see much of, but you will see it in how colors are described in HTML markup language for the internet, web design. If you're doing web design and you want to define a color, you define it with a hexadecimal number representing 0 through 255 possible states for each of 3 channels, red, blue, and green. So you will see hexadecimal numbers there, and when we get into Photoshop or Illustrator, I'll show you where that is. Hexadecimal, your digits are 0 through 9, A, B, C, D, E, and F. So F is 15. 16 would be expressed as 1, 0. 17 would be expressed as 1, 1. Because it's a zeros column, a ones column, and then a 16s column. Decimal 10 equals 110 and no ones. Hexadecimal 10 equals 116 and no ones. 155 in hexadecimal would be 9b. That's 9 times 16, which is 144, plus 11, b. 9, 10, 11b. Keyboard input is by 8-bit alphanumeric on most computers, and they are ASCII keyboards, American Standard Code for Information Integration. There's also an EBCDIC keyboard. I haven't seen one used in some word processors or some other systems years ago, but I really haven't come across anything that's in EBCDIC. Most of it is ASCII. There is also 16-bit alphanumeric, which is called Unicode, and Unicode using 16-bit is capable of a wider range of possibilities than you can actually fit on an 8-bit keyboard, and we'll talk a bit about that later. So these are common terms for sizes of data or sizes of storage of data. SI is the International System of Units, SI abbreviated from the French Système International d'Unités. This is the modern form of the metric system. So here are the names. Kilobyte, you probably heard of kilobytes. You may have data or file sizes or memory in kilobytes. Popularly, that's 2 to the 10th. The standard SI would be 10 to the 3rd. So 2 to the 10th is actually 1024. Standard SI, 10 to the 3rd, would be an even thousand. Megabytes, 2 to the 20th or 10 to the 6th. So this is kilobytes is 1,000 bytes, megabytes is 1,000,000 bytes, gigabytes is 1,000,000,000 bytes, and it goes up from there. Terabytes, 2 to the 40th or 10 to the 12th, petabytes, exabytes, etc. And it may be a while before you see computer storage that you have access to in some of these larger numbers, but rest assured they already have names for them. So these are the SI prefixes. This is the binary prefixes. So some people would call it a kibibyte as opposed to a kilobyte. Size, approximate storage capacity. 1 byte, a single character. 10 bytes, a word or two. 100 bytes, a sentence or two. 1 kilobyte, a very short story. 10 kilobytes, an encyclopedia page, perhaps with a simple picture, and it's got to be a really simple picture. 100 kilobytes, a medium resolution photograph. That's relative to your point of reference, I guess. Most of the medium resolution photographs I deal with are considerably larger than 10 kilobytes, although for a black and white that's say used on the internet or in a newspaper, 10 kilobytes might be okay if the photo isn't too large. 1 megabyte a novel, 10 megabytes 2 copies of the complete works of Shakespeare, 100 megabytes 1 meter of shelved books, 1 gigabyte a pickup truck filled with pages of text, 1 terabyte 50,000 trees of paper, and 10 terabytes the printed collection of the U.S. Library of Congress.